Hello and welcome to this video. In this video we are going to do some revision. This revision can be typically useful for undergraduate civil engineering students studying foundation. Usually if you're watching from anywhere else, because in the Kenyan system this is in fourth, fifth year there, and in your own system you can check to see where this content can fit, but generally for undergraduate students, depending on at which stage do you do this kind of work. So this is two of them is about design of retaining walls, and then one last question is about consolidation. So only three questions, and this can also be useful for, I think, graduate level students as well. Welcome. I hope you find something useful for you here. So figure 1 shows a cantilever sheet pile wall penetrating granular soil. Here L1 is 5 meters, L2 is 3 meters, gamma is 15.9 kilonewton per meter cubed, and gamma sat, the saturated unit weight, is 19.33 kilonewton per meter cubed, and phi prime is 35 degrees. So we are asked what is the theoretical depth, and here we are supposed to use CP2 method, so just so that you can see the figure. And like I've said, this content is at undergraduate in the Kenyan system, is specifically in fourth year, around fourth year there. And there's the CP2 method, there's a BS 8004 method, now Eurocode, and but the design is the same. It depends on the factors that you use to modify the shear strength of the soil. So that is what leads to CP2 method and the BS 8004 and so on and so forth. So depending on the assumption, but in this specific case, we have been told to use the CP2 method. So once you have seen the question, so there's some model answer there for you, so you can see. So here we lay out the given information, and then of course we know that D is 1.2 D naught. This is a gross pressure method from this is some background. This requires some background knowledge from the curriculum or from the content. So this is something we know. Then of course we also know that the sheet pile, we can use the Jenkins method. So here the coefficient of active earth pressure is tan squared 45 minus 5 prime over 2. That gives you 0.27. And then the coefficient of active earth pressure is tan squared 45 plus 5 prime over 2 gives you 3.69. So if you substitute phi is 35, you get these values. Then we know the relationship between the vertical stress and the horizontal effective stress. So vertical effective stress and horizontal effective stress. So to get the vertical effective stress on the active side, the reference is 0.0. So that would be 5 times 15.9, because as you can see the height there is 5. So at 0.0 there would be 5 times 15.9 plus 3 times 9, is it 9, the 19.3. So 5 times 15.9 plus 3 times 19.33, of course minus, because we are talking about effective stress, minus 9.81 times 3, and plus again 19.33 times d naught, minus 9.81 times d naught. So this is what we have laid down here in detail. Okay, so you can do the calculation. I think should not be difficult. Then to get the horizontal one, you have to multiply by Ka, so 0.27 times Ka. So this expression, because you don't know what d naught is, you can only have that expression. So, but because we're talking about stresses, the unit is kilonewton per meter squared, but we are talking about a unit meter in the direction perpendicular to the eye or perpendicular to the slide. So this is why we express kilonewton per meter squared per meter. On the passive side, the same logic. So on the passive side, the length is just d naught. So 19.33 d naught minus 19.8 d naught, so 9.53 d naught. Again, the horizontal stress on the passive side is Kp times the vertical stress on the passive side, which is 3.69. That solves to that. 35.17 d naught kilonewton per meter squared per meter. So we can derive the pressure distribution diagram on the active side and also on the passive side. The force on the passive side would be Pa, and the acting at, because these are triangular distribution, act as at the height divided by 3s has been shown. So on the passive side as well, so the center of action is at the height divided by 3. So to get the Pa, the stress or the force on the passive side is the area of the active, so the area of this, which is a half base, is 29.81 plus 2.57 d naught times height. So half times base times height, that's what we've done. And you can do your manipulation and find an expression in terms of Pa. Then the moment, excuse me, then the moment is the force times the lever arm. A lever arm as shown is 8 plus d naught over 3, so that's the moment on that side. So you can do the substitution. Okay, that's just arithmetic, which you can do in your own way. The expression myself, I got this expression for MA, alright. So in the CP2 method, again, we have to apply a factor of 2, of safety of 2 to the passive side. So the actual value here should be 35.17 d naught over 2, because we need to apply a factor of safety of 2 for the passive resistance. So this is what we do here. Half base times height. Height is d naught, but times a factor of safety of half. So that's the idea there. And the moment is the force times the moment arm, d naught over 3. That gives us 2.93 d naught d naught cubed. And then we know that if you sum the two, because those are the only forces there, not forces, the moment, they should be 0. Therefore, if you say that MA is positive and MP is negative, the moment on the active side is positive and the moment on the passive side is negative. So depends on you. You can reverse them as long as your sign convention is consistent. You should be fine. Then you can add and then get an expression 1 shown there. So this is a cubic equation which you should be able to solve in theory. So you can solve by trial and error. You can use any non-programmable calculator. For example, Casio FX991 EES plus should be. So in an exam, I think in practice, you should be able to solve it by any means if you have a computer, you know. But for the purpose of exam, I'm speaking specifically to Kenyan students because programmable calculators are not allowed in the exam room, but there are other calculators that are non-programmable, so you can use to solve. So anyway, whichever method you can use, that's just maths. So in my case, I get d equals 10 or negative 2.7, but negative values don't make sense here, so we ignore and then we take d naught is 10, and d is so d then is 12 based on d is equal to 1.2 d naught. Now, if for some reason you forgot to apply the factor of safety of half, you get the values shown there. But of course, that's not correct because you have to lose some marks. But this is how fair we mark, because we can consider sometimes that if you get the principle, of course here you'll have to lose some marks if you don't apply the safety factor specifically. So this is for CP2 method, you have to apply that half. Otherwise, If not, there are other scenarios where you don't have to apply the half, and therefore this can also be correct. So when marking, then all this is considered, just to make sure we are fair to everyone. So that's question 1. Question 2 is about designs of not design, okay, to get some factors of safety. So the cross section of cantilever was shown in figure 2. Calculate the factor of safety with respect to overturning, sliding, and bearing capacity. The bearing capacity is 567.41 kilonewton per meter squared. And this is what is shown. This is what you need to calculate. Okay, so the slanting, all right. So because there is some slope there, ranking method of getting the earth pressures is not very suitable. All right, so because there is some slope there, but this is the cross section how it looks. So to make this easier, we've given you a table where you can get Ka. So if you check the table, alpha there is 10. Alpha is 10, you can see there. So when alpha is 10 and phi is 35 is 30, yes, okay. So alpha is 10 and phi is 30, you get Ka as 0.3495, or you could use the Rankine, not the Rankine, the Mohr-Coulomb formula, if you remember it. So this is what we've done there, and get Ka as 0.3495. Then you can get the height, that's just trigonometry, you get 7.158 meters. Then you know the force is the area, which you can comes to about 161.17 kilonewton per meter. And then you can, because there's some slope there, you can get the vertical and the horizontal, or the component on the active side. And so that solves that. Then because we are supposed to find the factor of safety against overturning, so then we are supposed to find the moment. So here we are only dealing with either horizontal forces or vertical forces. All right, vertical forces and horizontal forces, so you can find the moment. So because these are gravity wall, you can divide them into sections shown. So for section 1, the area, and of course the weight is the area times the and of course should be times the volume in reality, but in fact we are assuming in the direction perpendicular to your eyes, that is 1 meter. So in fact this area is the same as the volume, right? So then the weight would be the volume times the unit weight, which in my case I've assumed 24. And some people can assume, I think the weight of concrete is usually between 23 to 24 there, so I've used 24. And the lever arm, so I'm just going to demonstrate to you one there. So and then the most important thing here also is where is where are you taking the moment. So is shown on at point C, so the moment is at point C. So if you take for example 1 at the section 1 is this one, section 1 is this one. So the is at the midpoint, which is 0.25, 0.25 plus, so this section here is 0.2, so 0.7. If you work out the base of this section 2 is I think 0.2 meters, so that's 0.9 plus 0.25 is 1.15. So the center, so the centers of these sections based on point C. So we are taking, we could take anywhere else, but we are taking, so for now we are taking the moment at point C. So if that is the case, so it's just geometry, so you don't forget about the rules of the centers and the distance from the centroid. So again this, so that's the volume, and the lever, I mean the volume and the weight, the lever arm, you can get that. Section 3, so you can scrutinize each of the section, each of those section, and see whether that makes sense. So the weight, and the moment, again, section 4, the weight, which translates to the volume, and then the moment, and section 5. And don't forget about the vertical force, all right, and then the point of action. So you sum the moment, so this becomes the resisting moments, and this is the total vertical force. So don't forget, because this is there's the soil, right, part of the soil, and also the sections of concrete. So the part of soil, I think, is the one, part 4. So let's see. So don't confuse the unit weight of concrete. So yeah, section 4 and 5 will use the unit weight of soil, and the rest of the sections will use the unit weight of concrete. At this how to get the center is just, these are just triangles. For example, here the centroid of section 2 is 2/3 from this edge, if you can see where I'm pointing. So it should not be very difficult to get the center, or to figure them out. So once you are able to do this, so this becomes the resisting moment once you add, because it uses its self-weight as part of the resisting mechanism. So you add the moments, that is the resisting moment. The overturning moment is the moment from the passive, from the active. So the horizontal force was 158.72 times the distance to the the point we are considering. So if you are considering here, all right, this is the toe. Is it the heel or the toe? And then the force is pH, the horizontal one. I think that should be pH. So the horizontal, and it should be this is a triangular distribution, so assume to be acting at h over 3, just like we've done before. So if there's a triangular distribution there, and the value is 158, is acting at the overall height. No, triangular distribution from there, acting at h, the overall height, divided by 3. So the result of that is the force times the height was 7.1 something, let's see. So 158.72 times 7.158 times 3. So that is the driving moment. So therefore you can balance out and see, of course, the overturning moment, the resisting moment are more than the overturning moments. Gives us a factor of safety of about 2.988, so that's good. Now for sliding, please take care of the following, that usually passive resistance is ignored unless you're told, but of course passive resistance will have some stabilizing effect, will contribute to increasing the overall shear strength of the soil. So uh, so you can ignore it. That's also um, valid, but if you do that, you're having conservative design. So here calculations have been done in three ways. You ignore the passive because the question was not clear unless you are told specifically. So you can ignore the passive resistance, or you can include it, and in this diagram is quite specific on the depth of the um, passive resistance. And then the depth the depth is given there, or sometimes the depth is just the same as the thickness of the base, or I mean of the base plate. All right. So the calculation is done based on the three assumptions because the question was not clear. Otherwise, if the question is clear on whether you can ignore or include the passive resistance, then you have to do what the question says. So we do this just to be as fair and as inclusive as possible. So if we ignore the passive resistance, so we know that the shear strength of the soil is C prime plus sigma V, the stress, the vertical stress basically times tan phi. But remember, so this is what we were saying about this is what makes the difference whether this is a CP2 method or BS8004 method, on the assumption of the interaction between the structure and the soil. So in this case, it's a reasonable assumption to assume that the effective friction, I mean on cohesion, are 2/3 of the C and phi values from the soil. So also note that the C and phi values here used here in if the properties of the soil are different, so these are C5 values of the foundation rather than the embankment soil. So you can see the C5 values of the foundation and the C5 values of the embankment soil are different. So you have to use the C5 values of embankment, or no, of foundation rather than embankment soil. So now the once you make these assumptions, then you can calculate the first one. We are ignoring the existence of the passive resistance, and because if the cohesion is given per unit length, then you have to multiply by the length. So 4 is the length of the base times the effective values, and you substitute as shown, and that gives you shear force of 2 point, or resistant force of 218.79 versus uh, the horizontal or the active earth pressure. So gives you a factor of 1.38. So these ones depend on if there is a standard you're comparing against. If, for example, the factor of safety against sliding is 1.5, then you can see this is less. But also you can see based on the assumption that we made. Again, if we assume that passive resistance is included and the depth is 1.5 as given in the uh, excuse me, as given in the diagram, then of course the calculation for the other parts are the same. The only difference is to calculate the passive earth pressure uh, because there is no slanting on the passive side, so we can use the Rankine uh, uh, formula to calculate Kp. So the passive resistance is about 215. If you add to the initial strength of the soil, you get 433, in which case the factor of safety is 2.73. So if you are using, for example, 1.5, you can see the factor of safety now is quite satisfactory. But the reason why you can ignore the passive earth pressure, you can see, you remember the CP2 method tells us that we have to apply a factor of safety because it's in doubt whether the entire passive earth pressure is going to be fully mobilized. So it depends on your assumption. So again here, again finally, if we assume the passive resistance is only by the base of this slab, then you can find the passive resistance based on D of 0.7, you get 89.48 plus the initial value 308, and you get a factor of safety of 1.94. So here, the any of this can be a reasonable way to do this, unless you are told that specifically that the passive resistance is can be ignored or can be included in the calculation. So this is for the logic. In practice, in fact, you can ignore the passive resistance. That means you're going to come up with a conservative design, which is safe. So the three scenarios have been put there for you for knowledge, but also the various design um, standards will give guidance on what is done in practice in various jurisdictions. And then for bearing capacity, we know this formula that V over B plus 1 into 1 plus or minus 6E over B. And then to find the eccentricity, they find the differences between the moments, whether it's resisting or overturning moments divided by the total overall vertical force, the difference between half of the base, that is your eccentricity, which is about here 0.412 meters. Then you ignore because it's plus or minus. Minus will give you the least and plus will give you the highest. But also you should care about the on that other side the least, because if it goes to the negative side you're in trouble. So you need to check whether this is less than B over 6. So in this case there are no tensile stresses. So once we check that E is less than B over 6, we are fine. If it were more than B over 6, then you have to check about the tensile forces, whether they exist, because we know, of course, concrete is weak in tension, which civil engineering students should know this. Otherwise, the bearing capacity is 567.41 divided by the maximum 191 gives you a factor of safety of 2.97. About 3, which is satisfactory because a bearing capacity of the bearing capacity factor usually is about between 3 and 6. So depends on, and sometimes can go even up to 2.5. Depends on how important your structure is, and then the factor is increased. So if for example, your code says that the factor of safety should be at least 3, then you can see this is just about there. So that's a good value, can be acceptable. But please make sure you refer to your own codes in your own countries or your own various jurisdictions. Then finally, a laboratory consolidation test. This is question 3 on normally consolidated clay showed the following results. So at 140, the void ratio is 0.92, at stress of 212, 0.864. The specimen was 25.4 millimeter, this 1 inch thick, drained on both sides. The time required for specimen to reach 50% consolidation was 4.5 minutes. So like so this one also requires some background information. Usually you do the odometer test or 1D consolidation test in the lab and use the result to solve an actual problem. So here again, a similar clay in the field, 2.8 meter thick, drained on both sides, subjected to similar increase, 140 to 212. Determine the expected maximum consolidation, the amount of time required to reach 40 total settlement of 40 millimeter in the field. Assume initial, millimeter, some problem there, but 40 millimeter. Assume initial increase in excess pore water pressure with depth. So we need also to know some way or the depot excess pore water pressure distribution to help us solve this problem. So like I said, this needs some background information that you should know. So we're just going to use some formulas here. You can refer to standard books, like for example, the Foundation Engineering is it Darcy? I'll show you. You can refer to anyway. Foundation Engineering books should have this information if you have no prior information about some of these formulas. So we know that to get the coefficient of compressibility, you can find the differences in the void ratio over the log of the. So this is just the virgin consolidation line. If you have some background information, so the gradient. So you need to find the potential change in the void ratio expected in the field. So that's what you use to get the coefficient of compression, which you find as 0.33. So for normally, because the question is very clear on normally consolidated case, so this formula of to get settlement is different based on whether it is normally consolidated soil over consolidated soil, and also is important whether the soil is in the initial condition is normally consolidated. After you apply the additional load, this delta sigma, does it remain normally consolidated, or it was initially over consolidated? After the additional load, you add the additional load, then it becomes uh, normally consolidated. So when it comes from over consolidated to normally consolidated, then you have to use also coefficient of swelling and add the two formulas. So anyway, the point is this formula is different whether the soil if the soil is normally consolidated and remains so after the additional load, or is over consolidated and remains as over consolidated after the additional load, or initially is over consolidated and crosses over to normally consolidated after the additional load. So but the question is very clear, so this is what we do. So 0.33 divided by 1 plus E naught. All this information is given to us. The depth is 2.8 meters, so whatever value we come up with is in meters, which are about 87.5 millimeter. So this is assuming 100% consolidation is 87.5. So we are asked the degree of 40. How long does it take to reach 40 millimeter? So if 100% would be 87.5, how much is 40? 40 divided by 87.5 times 100, about 45.7%. Then we know that the time factor is CV times the drainage path divided by T. So we are going to use this formula in two ways to get CV, because we don't know what CV is. So we were told that if to reach 50% consolidation, the time takes about 4.5 meters. The question told us this. So then we can substitute, and we know when consolidation is less than 60%, and the time factor is calculated as with the formula shown. So if the average consolidation is greater than 60, there's another formula which you should you can find in reference books. So because this consolidation is less than 60, the time factor for 50% consolidation. Remember, this we are only talking about 50, not the 45 we have calculated. So it's about 0.197. So because we know the time there, and this formula requires the time, then you can substitute in this formula to get the CV. All right. So once you get so 0.197 CV, which you don't know, and then take 4.5, then the drainage path is usually half. If there's two-way drainage, then the thickness of the layer is divided by 2. So this is what we've done, 25.4 divided by 2. This is how it gets. and then you get CV as 7.06 millimeter squared per minute. Then now go back to the 45% consolidation. So for the time factor to reach 45.7, the time factor is about 0.164, and then now applying this to the actual case, which is the drainage factor is half, should be half. The height is the height of the layer is 2.8 meters, or 2,800 millimeters. So then the drainage path is half. I've said this. Again, you substitute in the formula, and because this is the time that we don't know CV, we already know, because when the experiment is done, we're doing it to get CV and use it to solve the actual case in the field. Because in the experiment, you know the time, but the time in the experiment, because the thicknesses are different, right? So the experimental values are helping us to get things like CC and CV. So once we get CV, the time in the field we don't know. The time in the laboratory we know. So the time, based on the time and the changes in the laboratory, we can use that to get CV, right? All right. But in the field, then we don't know the time, but we have parameters from the lab. So we know CV, the thickness. Again, we substitute in this formula, you get a time of about 45,529 or 45,530 minutes, translates to about 759 hours or 31.62 days. So this is important because it tells you how long. So to get 45% consolidation, is it for about 46%, you need 30 days. So to get 100%, you need at least 2 point times, it's about 65 days, I don't know, 65, 70 days. So this is how useful these calculations are. So I hope this is useful to you, and goodbye. See you next time for other videos.